Hello, and thank you for watching. My name is Matthew Van Ginnep, and today I'm going to introduce a wonderful new machine developed by A&D called the Dynamic Contact Force Test Rig, or the Dcfr for short. Now this machine can measure dynamic contact patch forces under high speeds and in reproducible conditions. In this video, I'm going to briefly go over an introduction of what the Dcfr is and why contact patch testing is important. I'm going to then go off onto testing methodology, talking about the sensors that are involved in the Dcfr and how we're actually putting together the contact patch. After that, I'll go over some preliminary testing, first talking about test conditions and then actually going through the results. And then lastly, I'll conclude with a brief summary of key observations and discussion about future work. We live in an ever-evolving world. Even looking at vehicles, now electric vehicles are commonplace and self-driving cars are right around the corner. And tires need to evolve in order to keep up with the increased set of demands. I mean, so much has been done in developing new rubber compounds, work on tire tread design, increased manufacturing for environmentally friendly tires, and tire modeling itself. There's so much work going into that to try to understand how forces are generated on the tire. And of course, these forces all occur at the point of interaction in between the tire and the ground, also known as the contact patch. Now, contact patch testing has been around for many years, but it's always been limited in some way or another. It's generally been limited to slow speed maneuvers, relatively small forces, but now, with the Dynamic Contact Force Test Rig, you can test the contact patch dynamics under high speeds and in reproducible conditions. What makes this possible is use of the force matrix sensor, or the FMS for short. The FMS is a small component array of 4mm by 4mm sensors arrayed in a line. Each measures force in three directions: longitudinal, lateral, and vertical. It was originally designed to be embedded in the road surface so that a real vehicle could drive over it, it could measure the contact patch forces and recreate the tire contact patch. However, since it is just a line of sensors, what happened was, as the wheel is rolling over it, it's not able to actually measure the entire contact patch area, but rather it takes a slice of the tire and measures it the entire way through, and then reconstructs that in order to get an approximation of the contact patch. Now, while this is quite accurate, we lose a lot of details, such as tread design, for instance. The solution to that was to embed the force matrix sensor in a rolling drum machine. What this does is it simultaneously solves most of our issues from the previous slide. Now we can test under reproducible conditions, we can specify input test conditions, and due to the method of data processing, which I'll talk about in just a few slides, we can actually capture all the influences of tread design and tire defects as well. Now note that we have considered the effects of a rotating sensor, so we've already taken all of that into consideration. So this is the final machine that was developed, the Dynamic Contact Force Test Rig. A number of specifications are over here to the side. Ultimately, you can test up to speeds of 85 miles an hour. Maximum load is 10 kilonewtons. It can go plus or minus 20 degrees slip angle, and it can go from -5 to plus 30 degree camber angle. Also note that there is a standard 6-component force sensor at the tire spindle itself. So not only will it measure the 3 components of force at the tire surface, but you also get all 3 forces and all 3 moments at the tire spindle. Now I'm going to take a minute to go over the methodology for how to actually create the contact patch. So as the drum rotates, the FMS actually passes over the tire surface at relatively arbitrary points. And as it does so, varying data points are captured and combined so that eventually we get this 360-degree snapshot of the tire surface. Imagine chopping the tire and rolling it out, and what you get here is the entire circumference of the tire from 0 degrees to 360 degrees. And we found that around 3,000 rotations are necessary to capture over 90% of the data required. And I'll get in a few slides, I'll talk about why 3,000 rotations was chosen. Now, as the FMS rotates, it's not just measuring the contact patch at one single point, but rather throughout the entire contact patch, from leading edge, middle, trailing edge, and many, many points in between. The Dcfr can measure up to 50 kilohertz, so you can actually measure many, many points in between these ones here. And this is similar to what it does when it's actually on the road surface, how the tire rolls over and it's actually measuring through the entire contact patch and puts that together as an approximation. But here, since we're able to keep steady state conditions, we're actually able to get full 360-degree snapshots at every section along the contact patch. And that leads us to this slide, where what we have here are the three kind of contact patch areas from last time. What we do is we geometrically align them over here, so that here we have data from the leading edge, from the middle, from the trailing edge, and many, many points in between that then combine together in order to actually produce the contact patch. And this is an extremely accurate representation of what's actually happening at the contact patch. Now note that due to this method of data processing, we can only test in steady state conditions, right? Because each of these data points is taken at a different time. You might have one taken at rotation 30, one at 2000, and another one at 1546 for all I know, right? So during each of these rotations, we want to keep the dynamics as constant as possible. And lastly, I want to touch on resolution of the sensors. Along the lateral direction, our resolution is fixed at 4 millimeters, and that's obviously because of the size of the sensor. If you wanted to increase this resolution further, you could add another array of force matrix sensors along there, slightly offset by 2 millimeters, which then would, of course, increase your resolution to 2 millimeters. Along the longitudinal direction, the resolution varies, right? If you run the drum for very few rotations, you may get gaps in data leading to poor resolution, or if you run it for a very long time, you could get overlapping data, which then would increase the resolution of data. We interpolate between all data points, and we found that around 3,000 rotations gives us very good accuracy in the longitudinal direction. For the set of tests that I'm about to show, our average resolution of our longitudinal data was 1.5 millimeters, which we think is pretty good. You could test for an extra 4 or 5 hours and only increase resolution by another 0.5 millimeter. So we found that 3,000 rotations was a good kind of middle ground in between test time and resolution. So now let's move on to the actual tests that were performed, starting with test conditions. So we decided to actually look at differences due to tread design on tire patch dynamics. We took a 205 55R16 tire and manually altered it by adding sipes. So these are all the exact same tire, but here we added 3 additional longitudinal sipes, and here we added sipes in the lateral direction as shown by these figures. And for each tire, we tested it under 7 different scenarios, each varying only a single test condition. We varied speed, vertical load, slip angle, and slip ratio. We decided for these sets of tests not to vary camber angle. So now let's move on to the actual results. And I'm going to be talking about 4 main tests, 2 varying test conditions to see how it influences tire dynamics, and then 2 actually looking at different tires and how the tread design varies the contact patch dynamics. Here's an example of the type of data you'll be seeing in the next few slides. What you see here are the contour plots of the dynamics at the contact patch. Here we're showing only the normal force for the test condition at 4 kilonewtons and at 2 kilonewtons. Here we see summaries along the direction. So what you see here is basically a sum of data along these rectangles shown here, and then here you see some of data along the longitudinal direction there. And what you can tell is each of these blue lines represent blue color here for 2 kilonewton tests, and then the red lines for the red title being the 4 kilonewton test. So this is a test for normal load change. So we have the 4 kilonewton test and the 2 kilonewton test for longitudinal force, lateral force, and vertical force. And of course, one thing we see right off the bat is an increase in contact patch size with normal load as expected, and also an increase in magnitude of forces, which is also expected as we're increasing normal load. But some other observations of point, what we see here is a slight shift in contact patch along the lateral direction, and this is likely due to the asymmetric rigidity of the wheel, and so force distribution along that direction is not quite constant. We also see that in this point right here, along where the force transitions from positive to negative force, it's approximately the same for both scenarios, and that of course means that this is not highly dependent on normal load. This is a comparison of different speed changes. We have a 30 kilometer test, a 60 kilometer per hour test, and a 100 kilometer per hour test. Note that for each of these tests, the slip ratio is 0, so the wheel is free rolling. The only thing that's changing is the speed of the test. Once again, we have longitudinal force, lateral force, and vertical force. And here I wanted to show that we get an increased normal load at the shoulders, right? So we think that as the tire is spinning more, the centrifugal force is higher, which then pushes the tire, makes it slightly stiffer. We get increased forces at the shoulder. We also see a slight reduction in contact patch size, which is also likely due to the increased stiffness of the tire, allowing less deformation. What we see here is actually a little different from the previous slides. This is actually a comparison between the 100 km/h test and the 30 km/h test. So I've actually taken the data and subtracted it from the 100 km/h test. And here you can really easily see the reduction in contact patch size at the leading edge. You can see the increased forces at the trailing edge. And then you can also see these lines represent the center of force position. So you can see the center of force move slightly towards the trailing edge, which makes sense due to the reduction in contact patch size at the leading edge and the increased force at the trailing edge. So now let's move on to changing our tires, right? So now we have our stock tire, no alterations, longitudinally sloped tire, and laterally sloped tire. And this is for the side slip test, right? So this test is stock. Same normal load, speed, everything as this test, only this test has a 2-degree slip angle. What we see here is first off, contact patch shift slightly due to tire stiffness. So both the longitudinally sloped and laterally sloped tires do have this contact patch shift from the stock tire. And we think that's because since we added these additional slopes, we're reducing the stiffness of the tire, allowing it to move into form more, which causes the shift. We also see that over on this side of the graph, our data is a lot more sporadic or different than on this side where it's relatively common. And that's just because, as you can see over here, our contact patch size is quite small. So the influences of tread design are quite limited. Whereas on this side, we can actually see, even in the contour plots, significant changes in poor distribution of force along these laterally sloped ones, and that's captured here. So I think there's a lot of useful information that can be seen. Also, lastly, I want to show that the lateral forces of the sloped tire actually shift towards the leading edge. And once again, we think this is hand in hand with tire stiffness. And then next, we have a very similar set of tests, except this is with a slip ratio test, a braking test. So once again, we have the stock, longitudinally sloped and laterally sloped tires. This is the same stock test, but this one, instead of having a slip angle of 2 degrees, now it has a 2% braking slip. And so there are a number of, observations to point out. First is with the laterally sloped tire, you can see, even right in this contour plot, and down here especially, you can see very significant changes in the forces, which can also be captured in these summary plots. Since we're adding additional slopes, we're allowing the tire to deform more than often, which then actually makes the distribution of force much more uneven. Also, since the longitudinal force or longitudinally sloped tire and the stock tire are very similar, for longitudinal tests, the longitudinal slopes actually don't have much of an effect. So if you look over here at the summaries, you'll actually see that they are very close, have pretty much the same peak force and very similar force distributions throughout. And so that's pretty much all the data I have to present for you today. Ultimately, we found that the tire dynamic contact patch forces can be quite accurately conveyed and measured through this machine. We can measure them accurately and repeatably. We're hoping that through this new technology, we can make further innovations in tire design or tire manufacturing in general, maybe even creating new tire models, right? There's lots of potential, and we're going to continue to work with this machine, investigating common phenomena such as rolling resistance, for instance, to see how this new information can lead to new insights, which can lead to new technology. Thank you very much for listening.